Simulation theory: are we living in a computer simulation? Part 1. Look around you. The chair you're sitting on. The screen you're watching. The room around you. The sky beyond your window. Everything feels undeniably real. Solid. Consistent. Predictable. We build our lives upon one simple assumption. Reality is exactly what it appears to be. But what if that assumption is wrong? What if the universe is not fundamental? What if everything we experience, every star, every galaxy, every atom, every thought, exists inside an unimaginably advanced computer simulation? It sounds like the plot of a science fiction film. Yet over the past 2 decades, this remarkable idea has become the subject of serious philosophical and scientific discussion. Leading physicists, computer scientists, philosophers, artificial intelligence researchers, even entrepreneurs in the technology industry have debated the possibility. Not because they possess proof, but because modern science has reached an extraordinary point. Technology is advancing so rapidly that questions once considered impossible have become worthy of thoughtful investigation. This idea has become known as simulation theory. It asks one of the most profound questions humanity has ever considered. What is reality? The search for an answer did not begin with computers. Nor did it begin with modern physics. For thousands of years, philosophers have questioned whether the world we experience truly represents ultimate reality. The first known discussions reach back to ancient civilizations. Among the earliest was the Greek philosopher Plato. Around 380 BC, Plato described one of history's most influential thought experiments: the allegory of the cave. Imagine a group of prisoners chained inside a cave since birth. They face a blank wall. Behind them burns a fire. Between the prisoners and the fire, people carry various objects. The prisoners cannot turn around. They see only shadows moving across the wall. Because the shadows are all they have ever known, they believe those shadows are reality itself. Now imagine one prisoner escaping. For the first time, they leave the cave. They discover sunlight, trees, mountains, the real world. Returning to the cave, they attempt to explain the truth to the others. The prisoners refuse to believe them. How could the shadows not be real? Plato used this story to illustrate an important philosophical idea. Human beings may mistake appearances for reality. What we experience through our senses might represent only a small part of something much greater. More than 2,000 years later, this ancient allegory continues influencing discussions about simulation theory. The cave has simply become digital. Another remarkable parallel appears in Eastern philosophy. Within Hindu traditions, the concept of Maya describes the material world as an illusion. Not necessarily false, but incomplete. Ultimate reality exists beyond ordinary perception. Similarly, many schools of Buddhism teach that our everyday understanding of the world is shaped by perception, attachment, and limited awareness. These traditions differ greatly from modern simulation theory. Yet they ask surprisingly similar questions. Can our senses be trusted? Is there a deeper level of reality? What if the world we experience is only one layer of existence? Centuries later, a French philosopher introduced another famous thought experiment. His name was René Descartes. Writing in the 17th century, Descartes asked an unsettling question. Suppose an all-powerful deceiver manipulated every one of your perceptions. Everything you see. Everything you hear. Everything you touch. Could you prove that any of it was real? He realized something extraordinary. Even if every perception were false, the very act of doubting required a conscious mind. This led to one of philosophy's most famous conclusions. I think, therefore I am. Descartes demonstrated that certainty begins not with the external world, but with consciousness itself. Nearly 300 years later, another philosopher proposed something equally intriguing. George Berkeley argued that objects exist only because they are perceived. Although few modern scientists accept Berkeley's conclusions literally, his work reminds us that perception and reality may not be identical. The world we experience depends upon how our minds interpret information. Modern neuroscience supports part of this insight. Our brains do not directly experience reality. Instead, they construct an internal model using signals from our senses. Light enters the eyes. Sound reaches the ears. Pressure stimulates the skin. The brain assembles these signals into the rich world we perceive. In a very real sense, every human already experiences a simulation. Not a computer simulation, but a neurological simulation created by the brain. This realization has profound implications. Reality, as we experience it, always passes through interpretation. The question becomes, how closely does that interpretation match whatever exists outside our minds? During the 20th century, physics introduced even stranger ideas. Albert Einstein revealed that space and time form a flexible fabric. Quantum mechanics demonstrated that particles behave in astonishing ways. Observation appeared deeply connected to measurement. The universe proved far more mysterious than classical science had imagined. Some physicists began wondering whether reality itself might resemble information. Not merely matter, but information. Bits. Patterns. Mathematics. As computers evolved, these philosophical questions gained new relevance. In the 1940s, the first electronic computers occupied entire rooms. Their capabilities were astonishing for the time, yet primitive by modern standards. Decade after decade, computing power increased dramatically. Machines once capable of only simple calculations eventually displayed photographs, videos, three-dimensional graphics, artificial intelligence, virtual reality, entire digital worlds. Video games became increasingly realistic. Players explored vast cities, entire planets, living ecosystems generated entirely by software. Millions of people interacted inside persistent online worlds. Some spent hundreds of hours immersed within digital environments. This technological progress prompted an extraordinary realization. If humanity's computers continue advancing, what might they achieve thousands, or millions, of years from now? Could future civilizations simulate an entire planet? A complete history? Conscious beings? Entire universes? These questions remained largely philosophical until one remarkable paper appeared in 2003. Written by Oxford philosopher Nick Bostrom, it would transform simulation theory from science fiction into one of the most discussed ideas in modern philosophy. Bostrom did not claim that we are living inside a simulation. Instead, he constructed a logical argument, a chain of reasoning, an argument that many respected scientists found surprisingly difficult to dismiss. Whether correct or not, it forced philosophers, physicists, and computer scientists to confront one extraordinary possibility. If advanced civilizations eventually possess unimaginable computational power, could reality itself be running on a computer far beyond anything we can presently imagine? That question would ignite one of the most fascinating debates of the 21st century. And it begins with mathematics. Part 2. In 2003, a philosopher at the University of Oxford published a paper only a few pages long. There were no equations describing black holes, no revolutionary discoveries in quantum physics, no claims that scientists had uncovered hidden evidence of a simulated universe. Instead, the paper presented a carefully constructed philosophical argument. Yet it would become one of the most discussed ideas in modern science. The author was Dr. Nick Bostrom. The paper was titled, "Are You Living in a Computer Simulation?" At first glance, the title sounded more like science fiction than academic philosophy. Many expected it to be little more than an entertaining thought experiment. Instead, readers discovered something unexpected. Bostrom was not arguing that humanity definitely lives inside a simulation. He was arguing that, if certain assumptions are true, the probability may be surprisingly high. His reasoning became known as the simulation argument. Notice the distinction. A theory proposes an explanation. An argument explores what logically follows from certain assumptions. Bostrom's paper belongs to philosophy, not experimental science. To understand the argument, imagine humanity continues advancing technologically. Year after year. Century after century. Eventually, thousands of years pass. Perhaps millions. Would such a civilization possess computers vastly beyond anything we can imagine today? History suggests the answer may be yes. Compare a modern smartphone to the first electronic computers built during the 1940s. Early machines filled entire rooms. They consumed enormous amounts of electricity. Yet they possessed only a tiny fraction of the processing power found inside an ordinary mobile phone. In less than a century, computing advanced by astonishing amounts. Project that progress forward another 1,000 years. Or 1,000,000. The possibilities become almost unimaginable. Now suppose an advanced civilization develops computers capable of simulating entire worlds. Not merely landscapes, but complete civilizations. Every city, every tree, every conversation, every historical event. Most importantly, every conscious individual. Could such a simulation become indistinguishable from reality? Bostrom suggested it might. He then introduced 3 possibilities. According to his argument, at least one of them is likely to be true. The first possibility is this. Almost all civilizations become extinct before reaching the level required to create realistic ancestor simulations. Perhaps they destroy themselves through war, environmental collapse, artificial intelligence, pandemics, or other catastrophes. If civilizations rarely survive long enough to develop such technology, then simulated universes would remain extremely rare. The second possibility is different. Advanced civilizations survive. They possess extraordinary computational abilities. Yet they choose not to create ancestor simulations. Perhaps they consider such simulations unethical. Perhaps they lose interest. Perhaps they devote their resources elsewhere. If nearly every advanced civilization refuses to build simulations, then once again simulated worlds remain uncommon. Then comes the third possibility. Advanced civilizations survive. They develop immense computational power. And they create enormous numbers of ancestor simulations. Perhaps billions. Perhaps trillions. If this occurs, the number of simulated conscious beings could vastly exceed the number of biological beings living in original civilizations. Imagine one real civilization creating 1,000,000 perfectly realistic simulations. Each simulation contains billions of conscious individuals. Statistically speaking, far more people would exist inside simulations than outside them. If that were true, and if conscious simulated beings cannot distinguish their reality from base reality, then any randomly selected observer would more likely exist inside a simulation. Not because anyone proved it, but because simulated observers would vastly outnumber original ones. This simple statistical reasoning became the heart of Bostrom's argument. Notice something important. The argument depends entirely upon its assumptions. If conscious simulations prove impossible, the argument collapses. If civilizations rarely survive, it collapses. If advanced societies refuse to build simulations, it collapses. The conclusion depends upon which assumptions ultimately prove true. This explains why philosophers continue debating it. Soon after publication, the simulation argument spread far beyond academic philosophy. Scientists discussed it. Technology entrepreneurs discussed it. The media embraced it. One particularly well-known supporter of taking the idea seriously has been entrepreneur Elon Musk. Musk has remarked that if computer games continue improving, eventually becoming indistinguishable from reality, then it seems plausible that advanced civilizations could create extraordinarily realistic simulations. He emphasized that this does not prove we live inside one, only that the possibility deserves consideration. Other scientists have been far more cautious. Many point out that current computers remain nowhere near capable of simulating an entire universe. Even today's most powerful supercomputers struggle with relatively small portions of physical reality. Simulating every particle in the observable universe appears unimaginably difficult. Supporters respond that future civilizations may possess technologies beyond our present imagination. Perhaps quantum computers. Perhaps entirely new forms of computation. After all, a smartphone would appear miraculous to someone living in ancient Rome. Predicting technology thousands of years into the future remains extraordinarily difficult. Another important question concerns consciousness. Could a computer truly become conscious? Or would it merely imitate consciousness? This remains one of philosophy's deepest mysteries. Some researchers believe consciousness naturally emerges from sufficiently complex information processing. Others argue that subjective experience requires something computers can never possess. Science has not yet answered this question. Without understanding consciousness itself, we cannot know whether simulated minds could genuinely exist. Another criticism involves computational limits. Would simulating an entire universe require more computing power than the universe itself contains? Some physicists suspect it might. Others suggest only the portions currently being observed require detailed simulation. Much like modern video games, a game does not calculate every blade of grass across an entire planet simultaneously. It generates detail where the player happens to be looking. Some simulation theory supporters suggest reality might operate similarly. This idea remains speculative. No evidence currently supports it. Yet it illustrates how advances in computer science continue influencing philosophical discussions. The simulation argument also inspired broader conversations about reality. If we cannot distinguish a perfect simulation from reality, does the distinction matter? Suppose every experience remains consistent. Every scientific law functions normally. Every relationship feels genuine. Would living inside a simulation make our lives less meaningful? Many philosophers answer no. Reality, whatever its ultimate foundation, remains the reality we experience. Love, friendship, discovery, beauty, suffering, achievement. Their significance depends upon conscious experience, not necessarily upon the underlying substrate producing that experience. Whether atoms or computer code. Still, the idea continues provoking intense debate. Not because evidence proves it, but because logic makes it difficult to dismiss entirely. The next question becomes even more fascinating. If advanced civilizations could create simulated universes, how close are we to developing such technology ourselves? The answer begins with one of humanity's most remarkable achievements: the computer, and the extraordinary pace of technological progress. Part 3. Imagine showing a modern smartphone to someone living in the year 1800. A device no larger than the palm of your hand, capable of storing millions of books, displaying moving images from across the world, calculating billions of mathematical operations every second, speaking to an artificial intelligence, navigating anywhere on Earth using satellites orbiting high above the planet. To someone from the 19th century, it would appear indistinguishable from magic. Yet this astonishing technology emerged in only a few generations. Now imagine what computers might become 1,000 years from now. Or 10,000. This question lies at the heart of simulation theory. Because if computing power continues advancing, could future civilizations eventually simulate entire worlds? To answer that question, we must first understand how rapidly computers have evolved. The story begins in the 1940s. During the Second World War, enormous electronic computers were built to perform military calculations. One of the earliest was ENIAC. It occupied an entire room, contained nearly 18,000 vacuum tubes, weighed more than 30 tons, consumed vast amounts of electricity. Despite its impressive size, ENIAC possessed less computing power than a modern pocket calculator. At the time, however, it represented a technological revolution. Engineers quickly realized that electronic computation would transform civilization. They were right. During the following decades, vacuum tubes gave way to transistors. Transistors became integrated circuits. Integrated circuits became microprocessors. Each breakthrough made computers smaller, faster, more powerful, and less expensive. In 1965, engineer Gordon Moore, co-founder of Intel, made an observation that became famous. He noticed that the number of transistors fitting onto a computer chip appeared to double approximately every 2 years. This trend became known as Moore's Law. Although not a physical law, it accurately described technological progress for decades. Computers improved at an astonishing pace. Processing power increased exponentially. Memory expanded. Costs declined. The digital revolution accelerated. By the late 20th century, personal computers entered homes. The internet connected billions of people. Then smartphones placed extraordinary computational power into nearly every pocket. Today, supercomputers perform calculations unimaginable only a generation ago. Artificial intelligence recognizes speech, translates languages, creates images, writes software, even participates in scientific research. Each achievement once belonged entirely to science fiction. Now consider another remarkable development: video games. Early electronic games displayed simple geometric shapes. A bouncing square represented a ball. A few white lines became tennis paddles. By modern standards, the graphics appear primitive. Yet each decade brought dramatic improvements. Three-dimensional environments emerged. Dynamic lighting, realistic weather, sophisticated physics, open worlds stretching across hundreds of square kilometers. Millions of players simultaneously inhabit persistent online universes. Some modern virtual worlds possess day and night cycles, complex economies, wildlife, artificial characters capable of responding intelligently to players. Entire civilizations exist inside computer-generated landscapes. As virtual reality technology advanced, immersion increased even further. Wear a modern virtual reality headset. Within moments, your brain begins responding as though the simulated environment surrounds you. You instinctively step away from virtual cliffs, duck beneath digital obstacles, reach toward objects that exist only as computer-generated images. Your senses become convinced. Although you know intellectually that the experience is artificial, part of your brain reacts as though it is real. Researchers call this phenomenon presence, the feeling of genuinely existing inside a virtual environment. As display technology improves, that illusion becomes increasingly convincing. Some futurists ask an obvious question: if virtual worlds continue becoming more realistic, where does the process eventually end? Perhaps future technology produces simulations indistinguishable from ordinary reality. This possibility grows even more intriguing when combined with advances in artificial intelligence. For decades, computers followed rigid instructions. They performed calculations exactly as programmed. Modern AI behaves differently. Machine learning systems recognize faces, compose music, generate artwork, hold conversations, drive vehicles, discover patterns hidden within enormous datasets. Large language models can answer questions, summarize information, and assist with creative work. Although today's AI remains fundamentally different from human consciousness, its rapid improvement has surprised many researchers. Some scientists believe artificial general intelligence, often called AGI, may eventually equal or exceed human cognitive abilities. Whether this occurs remains uncertain. Nevertheless, progress has been remarkable. Suppose a future civilization creates artificial intelligences possessing genuine consciousness. Those digital minds might inhabit entirely simulated worlds. They would experience their environments just as biological beings experience ours. If so, simulation theory becomes far more plausible. The simulated individuals would possess thoughts, memories, emotions, relationships, lives, all unfolding within a computational universe. This possibility introduces another fascinating concept: digital consciousness. Could the human mind itself someday be copied into a computer? Some futurists propose a process known as mind uploading. The basic idea appears simple. Map every neuron inside the human brain, every synapse, every electrical connection, every memory, every pattern of activity. Then reproduce that structure inside an advanced computer. Would the resulting system become conscious? Would it truly be you? Or merely an extraordinarily accurate copy? No one currently knows. Neuroscience has made tremendous progress understanding the brain. Yet consciousness itself remains one of science's greatest mysteries. Without understanding how subjective experience arises, we cannot determine whether uploading a mind would preserve awareness, or simply imitate it. Another important idea comes from information theory. Some physicists suggest that information may be even more fundamental than matter. John Archibald Wheeler, one of the 20th century's most influential physicists, proposed the phrase, "it from bit." According to Wheeler, physical reality may ultimately emerge from information. In other words, the universe may resemble a gigantic information processing system. Not necessarily a computer built by someone else, but a cosmos whose deepest foundation consists of information itself. This idea influenced later discussions about simulation theory. If reality already behaves like information, perhaps the distinction between physics and computation is smaller than we imagine. Quantum computing pushes these ideas even further. Unlike ordinary computers using bits that are either 0 or 1, quantum computers use qubits, which can exist in combinations of states according to quantum mechanics. Certain problems that would require millions of years for conventional computers may someday be solved in minutes by powerful quantum machines. Although today's quantum computers remain limited, researchers continue making rapid progress. Some wonder whether future quantum computers could simulate entire universes. Others argue that even quantum technology would face insurmountable limits. The debate continues. Still, one remarkable fact remains undeniable. Humanity has progressed from room-sized calculators to artificial intelligence in less than 1 century. If technological civilization survives, the next 1,000 years may produce advances beyond anything we currently imagine. This realization forms one of the strongest motivations behind simulation theory. Not evidence, not proof, but possibility. Yet another question naturally follows. If reality were truly simulated, would there be clues hidden within the laws of physics themselves? Could the universe already contain signs suggesting it operates like an unimaginably advanced computer? Some physicists believe the answer may lie within the deepest foundations of space and time themselves. Part 4. Suppose you zoomed in closer and closer to reality. Past your hand. Past individual cells. Past molecules. Past atoms. Past electrons. Would space continue forever? Smooth. Continuous. Infinitely divisible? Or would you eventually reach the smallest possible unit? A fundamental pixel of reality. This question has fascinated physicists for generations. If the universe behaves like a computer simulation, perhaps reality itself is built from tiny, discrete pieces. Much like the pixels on a computer screen. From a distance, an image appears perfectly smooth. Look closely enough. Individual pixels become visible. Could space and time work the same way? Modern physics provides a surprising answer. Perhaps. Although no experiment has yet confirmed that space is fundamentally pixelated, there are natural limits built into our current understanding of the universe. These limits are known as the Planck Scale. Named after German physicist Max Planck, they represent the smallest meaningful units that appear in many areas of theoretical physics. The Planck length measures approximately 1.6 times 10 superscript 3 meters. To appreciate how incredibly small that is, imagine comparing an atom to the observable universe. The Planck length is vastly smaller still. Many physicists suspect that below this scale, our ordinary understanding of space may no longer apply. Similarly, the Planck time represents the shortest meaningful interval of time. Approximately 5.39 times 10 seconds. Current theory suggests that asking what happened during intervals shorter than the Planck time may not even be physically meaningful. These values do not prove the universe is made from digital pixels. They simply indicate scales where existing theories cease to provide reliable descriptions. Yet they inspire intriguing speculation. If reality possesses a smallest possible length, could space resemble a digital grid? Some researchers have explored this possibility. Others believe space remains fundamentally continuous. The evidence remains inconclusive. Then there is another remarkable discovery. The universe appears astonishingly mathematical. Everywhere scientists look, nature follows elegant equations. Gravity, electromagnetism, quantum mechanics, relativity, planetary motion, light, atomic structure. All obey precise mathematical relationships. Why should mathematics describe reality so perfectly? The physicist Eugene Wigner famously referred to this as the unreasonable effectiveness of mathematics. It remains one of science's deepest mysteries. Some researchers argue that mathematics merely describes reality. Others wonder whether mathematics actually is reality. Simulation theory often builds upon this observation. After all, computers ultimately process mathematics. Digital worlds consist entirely of mathematical relationships. Perhaps our own universe does as well. Another fascinating idea concerns information. Physicist John Wheeler proposed that information may lie at the heart of physical reality. His phrase, "it from bit," suggested that matter, energy, and even space-time might ultimately emerge from information. In this view, the universe resembles a vast computational process. Not necessarily because someone programmed it, but because information itself may be fundamental. This concept has influenced several areas of modern theoretical physics. Perhaps the most surprising comes from black holes. For decades, black holes presented an enormous puzzle. According to Einstein's general relativity, anything crossing the event horizon disappears forever. Information included. Quantum mechanics, however, insists that information cannot simply vanish. The conflict became known as the black hole information paradox. For years, physicists debated the issue. Eventually, Stephen Hawking acknowledged that information likely survives in some form. Exactly how remains an active area of research. The debate transformed our understanding of black holes. It also highlighted something extraordinary. Information appears deeply woven into the fabric of reality. Another concept receiving enormous attention is the holographic principle. Imagine a hologram. Although appearing three-dimensional, all the information exists on a two-dimensional surface. Some physicists have proposed something similarly astonishing about the universe. Perhaps the information describing our three-dimensional reality is encoded upon a distant two-dimensional boundary. The idea emerged from attempts to understand black hole thermodynamics. It has since become one of theoretical physics' most influential concepts. Importantly, the holographic principle does not imply the universe is literally a computer simulation. Nor does it suggest reality is fake. Instead, it proposes an unexpected relationship between information and space. Still, supporters of simulation theory often point to it as another indication that information may be more fundamental than matter. Quantum mechanics contributes additional mysteries. The double-slit experiment, discussed earlier, continues challenging intuition. Particles behave like waves. Measurement influences outcomes. Probability replaces certainty. Some people interpret these behaviors as evidence that reality resembles computer software rendering information only when needed. This analogy appears frequently online. Scientifically, however, it is important to be careful. Quantum mechanics does not require the universe to be a simulation. Its equations accurately describe experimental results without invoking computers. The simulation interpretation remains speculative. Another observation sometimes mentioned involves the speed of light. According to Einstein, nothing carrying information can travel faster than approximately 299,792 kilometers per second. Some simulation theory advocates compare this universal speed limit to a processor's maximum clock speed. Perhaps the universe imposes computational limits. Again, this comparison is metaphorical. Modern physics explains the speed of light through the structure of space-time itself. No evidence currently demonstrates that it represents a computational limitation. Similar arguments involve quantum randomness. Some claim random events resemble computer-generated random number algorithms. Physicists generally disagree. Quantum randomness appears genuinely fundamental according to present evidence. Whether deeper hidden processes exist remains unknown. One recurring theme appears throughout these discussions: patterns, limits, mathematics, information. Each resembles aspects of computation. But resemblance alone does not establish identity. Clouds resemble cotton. That does not make them fabric. Careful science distinguishes analogy from evidence. Nevertheless, these ideas encourage fascinating questions. Could reality operate according to informational principles more profound than we currently understand? Could future discoveries reveal unexpected connections between computation and the laws of nature? Possibly. Many researchers continue exploring precisely these questions. At the same time, others warn against drawing conclusions too quickly. Modern physics already appears strange without requiring simulation theory. Quantum mechanics, relativity, black holes, dark matter, dark energy. Each remains extraordinary. Adding simulations introduces additional assumptions. Those assumptions require evidence. As yet, such evidence has not appeared. Still, many people believe they have personally experienced something unusual. A moment when reality itself seemed to malfunction. A strange coincidence. An impossible memory. A sudden feeling that something was not quite right. These experiences have become known by many names: glitches, déjà vu, reality shifts, simulation errors. Do they reveal hidden flaws within reality? Or do they simply reveal how remarkable the human mind can be? The next chapter explores these fascinating experiences. and separates psychology from speculation. Part 5. Imagine walking into a room. Suddenly, an overwhelming feeling washes over you. You've been here before. You know exactly what someone is about to say. For a brief moment, everything feels strangely familiar. Then, just as quickly, the feeling disappears. Most people experience this phenomenon at least once in their lives. Some experience it often. It is known as déjà vu. The phrase is French for already seen. For centuries, people have wondered what causes it. Is it a glimpse of another timeline? A memory from a previous life? A brief overlap between parallel realities? Or simply the way the brain processes information? Simulation theory has brought renewed attention to experiences like this. If reality were a computer simulation, could occasional glitches occur? Could tiny errors appear within the program? Many internet discussions suggest exactly that. But before considering extraordinary explanations, it is important to understand what science has discovered. Neuroscientists have studied déjà vu for decades. One leading explanation involves the brain's memory systems. Normally, incoming experiences pass through regions responsible for recognizing whether something is familiar or completely new. Occasionally, these systems appear to activate slightly out of sync. The result is a powerful, but false, feeling that the present moment has already happened. Brain imaging studies support this idea. Déjà vu appears to involve temporary activity within the temporal lobes, particularly regions associated with memory. It feels extraordinary. But current evidence suggests it originates within normal brain function. Still, the experience remains remarkably convincing. Many people leave such moments feeling that reality itself briefly shifted. Another phenomenon frequently connected to simulation theory is the Mandela effect. Millions of people confidently remember historical events, movie quotes, logos, or famous names differently from documented reality. Perhaps the most famous example involves Nelson Mandela. Some people vividly remember him dying in prison during the 1980s. In reality, Mandela was released in 1990, became president of South Africa, and passed away in 2013. Other examples include the spelling of the Berenstain Bears, the Monopoly Man's appearance, famous movie quotations, and brand logos. Supporters of simulation theory sometimes suggest these discrepancies represent evidence that reality has been altered. Perhaps the simulation was updated. Perhaps timelines merged. Perhaps memories remained while history changed. Modern psychology offers a different explanation. Human memory is not a perfect recording. It is reconstructive. Every time we remember something, the brain rebuilds the memory from stored fragments. Small inaccuracies naturally appear. When many people share similar expectations or cultural influences, they often reconstruct memories in similar ways. This can create large groups confidently remembering the same incorrect detail. Research into false memories has repeatedly demonstrated how easily memory can be influenced. In one famous series of experiments, psychologist Elizabeth Loftus showed that carefully worded questions could alter eyewitness recollections. Participants sometimes remembered events that never occurred. Not because they were lying. Because the brain genuinely reconstructed new memories. These discoveries transformed legal psychology. They also illustrated an important lesson. Confidence does not guarantee accuracy. Another phenomenon often discussed is synchronicity. The term was introduced by Swiss psychiatrist Carl Jung. Synchronicity describes meaningful coincidences that appear too remarkable to dismiss as chance. Imagine thinking about an old friend you have not spoken to in years. Moments later, they unexpectedly call. Or repeatedly encountering the same unusual number everywhere you look. Many people experience coincidences so striking they feel intentional. Simulation theory enthusiasts sometimes interpret these events as hints that reality contains hidden patterns. Perhaps the simulation subtly guides events. Perhaps unseen algorithms influence experience. Statistics, however, offers another perspective. Given billions of people living billions of lives, extraordinary coincidences become inevitable. Events that seem astronomically unlikely for one individual become surprisingly common across humanity as a whole. Our brains naturally notice unusual patterns while ignoring countless ordinary ones. This tendency is known as pattern recognition. Humans evolved to recognize patterns quickly. It helped our ancestors identify predators, locate food, predict weather, understand social behavior. The ability proved enormously valuable. Yet it also creates false positives. We sometimes perceive meaningful connections where none objectively exist. Psychologists refer to this as apophenia. Closely related is pareidolia, the tendency to see faces in clouds, animals in rock formations, hidden messages in random sounds. These experiences feel compelling because the brain is exceptionally skilled at constructing meaning. Simulation theory discussions often include reports of so-called glitches in reality. Stories circulate online describing impossible events, objects disappearing and reappearing, time seemingly stopping, people encountering identical strangers, buildings changing overnight. Some accounts are undoubtedly fictional. Others arise from misunderstandings. A few remain unexplained simply because insufficient information exists. Importantly, unexplained does not automatically mean supernatural. History contains countless mysteries later explained through ordinary investigation. Another frequently discussed phenomenon involves false awakenings. You dream that you wake up. You begin your normal morning routine. Then suddenly, you actually wake up. Sometimes several layers deep. The experience can feel astonishingly real. Some interpret false awakenings as evidence of alternate realities. Sleep researchers explain them through the complex transitions occurring between dreaming and wakefulness. Again, the experience is genuine. The interpretation remains open to debate. Modern neuroscience increasingly reveals that perception itself is an act of construction. The brain continuously predicts incoming sensory information. Rather than passively recording reality, it actively builds an internal model. Most of the time, this process works extraordinarily well. Occasionally, small prediction errors occur. Those moments can produce experiences that feel deeply mysterious. Simulation theory provides one possible narrative. Psychology provides another. Science attempts to distinguish between them through careful evidence. This distinction is crucial. Curiosity encourages us to ask bold questions. Evidence determines which answers survive. Many experiences associated with simulation theory are personally meaningful. They deserve thoughtful investigation. But meaningful experiences alone cannot establish how the universe fundamentally operates. Still, one fascinating question remains. Suppose simulation theory were actually true. Who created the simulation? Why would anyone build an entire universe? Would the creators resemble humans? Artificial intelligence? Future civilizations? Or something completely beyond our imagination? These questions move beyond physics into philosophy. And they lead us toward one of the most intriguing aspects of simulation theory. Not whether a simulation exists, but who, or what, might be running it. Part 6. Suppose, for just a moment, that simulation theory is true. The universe is not fundamental reality. Instead, everything we know exists inside an unimaginably advanced simulation. An obvious question immediately follows. Who built it? And perhaps even more importantly, why? This is where simulation theory moves beyond computer science and enters philosophy. Because if a simulation exists, there must, in principle, be something outside the simulation. A reality beyond our own. Nick Bostrom's original argument offers one possible answer. He suggested that the creators might be descendants of humanity itself. Imagine civilization surviving not merely for centuries, but for hundreds of thousands, or millions of years. Technology would almost certainly become almost unrecognizable. Today's supercomputers would appear primitive. Artificial intelligence might surpass biological intelligence. Entire planets could become computational centers. Energy sources beyond our current understanding might power unimaginable machines. Such a civilization could possess resources allowing it to simulate entire histories. Bostrom called these ancestor simulations. The purpose would be historical research. Imagine future historians wanting to understand 21st century civilization. Rather than studying ancient books, they create a complete simulation. Every city, every conversation, every historical event, every individual. The simulation becomes a living history lesson. Not merely recorded, experienced. If enough ancestor simulations exist, then statistically, simulated people might vastly outnumber original humans. This possibility formed the foundation of Bostrom's argument. Other researchers have imagined different motivations. Perhaps simulations become entertainment. Future civilizations might create entire universes the way modern people create video games. Some simulations could explore alternative histories. What if ancient Rome never collapsed? What if dinosaurs survived? What if humanity colonized Mars centuries earlier? Each simulation would answer different historical questions. Others suggest scientific research. Scientists today already use computer simulations to study weather, climate, galaxy formation, black holes, epidemics. As computers improve, simulations become increasingly detailed. Future researchers might simulate entire ecosystems, entire planets, eventually, entire civilizations. Another possibility involves artificial superintelligence. Suppose humanity creates an intelligence vastly exceeding our own. Such an intelligence might itself begin constructing simulations. Perhaps to solve scientific problems. Perhaps to explore possibilities. Perhaps simply because it can. Some philosophers argue that sufficiently advanced artificial intelligence might create countless virtual civilizations without direct human involvement. The simulations would become nested. A simulation creating another simulation, which creates another, potentially extending through many layers. This concept introduces one of simulation theory's strangest ideas. Suppose our universe is simulated. What if the civilization running our simulation also exists inside another simulation? And that one exists inside yet another? Reality could resemble an endless series of nested worlds, like mirrors reflecting one another forever. Whether such infinite nesting is actually possible remains unknown. Still, the concept illustrates how quickly philosophical questions multiply. Another fascinating topic concerns digital immortality. Many futurists believe one day it may become possible to preserve aspects of human consciousness digitally. Perhaps through advanced brain scanning. Perhaps through artificial intelligence trained upon an individual's memories, personality, and experiences. If successful, future generations might continue interacting with digital versions of deceased individuals. Whether these digital minds would truly possess consciousness remains deeply controversial. Yet the concept raises profound ethical questions. Would creating conscious simulations be morally acceptable? Suppose simulated beings experience happiness, friendship, love, fear, pain. Would they deserve rights? Protection? Freedom? If simulated individuals possess genuine consciousness, destroying the simulation could represent the destruction of billions of lives. Some philosophers argue that creating conscious beings solely for experimentation would become ethically unacceptable. Others believe sufficiently advanced civilizations would establish strict safeguards. These discussions closely resemble debates surrounding artificial intelligence today. As technology advances, questions once considered purely philosophical become increasingly practical. Another intriguing question involves communication. If creators exist, could we contact them? Science fiction frequently explores this possibility. Characters attempt to send messages beyond reality. Hack the simulation. Reach the programmers. In practice, no known scientific method exists. If our universe were simulated, the creators might deliberately prevent communication. Or perhaps interaction would simply be impossible. Some speculative thinkers have proposed unusual ideas. Perhaps mathematical constants contain hidden messages. Perhaps certain physical laws reveal signatures left by the creators. Perhaps unusual cosmic events represent external interventions. None of these ideas possess supporting evidence. They remain imaginative speculation. Still, they reveal humanity's enduring curiosity. If creators exist, we naturally wonder about their intentions. Would they resemble gods? This question leads simulation theory into theology. Some observers note intriguing similarities. Many religious traditions describe reality as intentionally created. Simulation theory also proposes an intentional creation. The similarities, however, should not be overstated. Religious beliefs generally involve spiritual, moral, and theological claims. Simulation theory proposes a technological possibility. The two frameworks answer different kinds of questions. Some individuals see harmony between them. Others view them as entirely separate. Science itself remains neutral. It neither confirms nor rejects theological interpretations. Its role is investigating testable claims. Another interesting philosophical question concerns meaning. Suppose tomorrow scientists somehow proved we live inside a simulation. Would anything truly change? Would friendship become less real? Would music lose its beauty? Would love matter less? Many philosophers answer no. Experiences remain meaningful because they are genuinely experienced. Whether reality ultimately consists of atoms, energy, information, or computer code, conscious experience retains its significance. Pain still hurts. Joy still inspires. Discovery still expands understanding. The foundation beneath reality may differ. The experience of living remains authentic. Perhaps this explains why simulation theory fascinates so many people. It challenges assumptions without necessarily diminishing human life. Instead, it encourages us to ask deeper questions. What is consciousness? What is existence? What makes something real? As remarkable as these philosophical discussions become, scientists continue asking a simpler question. If we truly inhabit a simulation, could we actually prove it? Could experiments reveal computational limits? Hidden programming? Tiny imperfections within reality itself? The next chapter explores the remarkable attempts researchers have proposed to test one of the boldest ideas ever suggested in modern philosophy. Part 7. Science advances through evidence. No matter how fascinating an idea may be, no matter how elegant the mathematics, no matter how popular it becomes, a scientific hypothesis must ultimately face the same question. How can we test it? Simulation theory is no exception. If we truly live inside an unimaginably advanced computer simulation, shouldn't there be evidence? Some detectable clue? A hidden signature buried within the laws of physics? Over the past 2 decades, physicists have proposed several intriguing possibilities. None has confirmed the theory. but each explores whether the idea can, in principle, be tested. One proposal begins with a simple assumption. Every computer has limits. Memory, processing power, storage. Even the most powerful supercomputer cannot perform infinite calculations. If our universe is simulated, perhaps similar limits exist here as well. Some researchers have suggested looking for the resolution of reality. Imagine enlarging a digital photograph. At first, everything appears perfectly smooth. Magnify enough. Individual pixels become visible. Could space itself possess an ultimate resolution? Modern physics already identifies the Planck length and Planck time as fundamental scales. Some simulation theory enthusiasts interpret these as possible pixels of reality. Physicists are more cautious. The Planck scale naturally arises from combining quantum mechanics with gravity. It does not demonstrate that space is digitally rendered. Still, if future experiments discovered unmistakable evidence that space consists of discrete computational units, interest in simulation theory would undoubtedly increase. Another proposal involves cosmic rays. These extraordinarily energetic particles constantly strike Earth's atmosphere. Some physicists have wondered whether their behavior might reveal computational limitations. In lattice simulations used today, continuous space is approximated using tiny grids. Such grids sometimes produce subtle directional effects. If our universe were computed similarly, extremely energetic particles might occasionally reveal preferred directions. Researchers have looked for such signatures. Thus far, observations remain consistent with ordinary physics. No convincing evidence of computational grids has been found. The idea remains speculative. Quantum mechanics provides another possible avenue. Some supporters of simulation theory suggest that the universe behaves similarly to a video game, only rendering details when necessary. They point to the double-slit experiment. Particles appear as probability waves until measured. Could reality simply delay computation until observation occurs? It is an intriguing analogy. But analogies are not evidence. Quantum mechanics already possesses mathematically complete explanations without invoking simulations. Current experiments do not require computer rendering as part of their interpretation. Another fascinating proposal concerns quantum computing. Today's computers process information using bits, zeros and ones. Quantum computers operate differently. Their qubits exploit the strange principles of quantum mechanics. Some researchers speculate that if reality itself operates like a quantum computation, studying quantum information may reveal deeper aspects of the universe. Importantly, this does not imply the universe is necessarily an artificial simulation. It simply suggests that information processing may play a fundamental role in physics. Another area frequently mentioned is the holographic principle. As discussed previously, this remarkable idea suggests that all the information contained within a volume of space may be encoded upon its boundary. Some enthusiasts compare this to computer graphics, a three-dimensional world generated from underlying information. Again, the resemblance is intriguing. But the holographic principle emerged from black hole physics, not from simulation theory. The two concepts overlap only indirectly. Then there is the idea of computational efficiency. Modern video games avoid calculating every detail continuously. Instead, they generate information dynamically. Only what the player currently observes receives maximum detail. Could our universe behave similarly? Some point to quantum uncertainty. Others point to wave function collapse. Yet once again, current physics explains these observations without requiring simulations. No experiment has demonstrated that reality renders itself on demand. One of the greatest challenges facing simulation theory concerns falsifiability. This concept, championed by philosopher Karl Popper, remains central to science. A genuine scientific hypothesis should make predictions capable of proving it wrong. Can simulation theory satisfy this requirement? Opinions differ. Some researchers argue that sufficiently advanced simulators could always hide evidence of the simulation. If so, the hypothesis becomes difficult, or perhaps impossible, to test. Others disagree. They believe future experiments may reveal computational artifacts impossible to explain otherwise. At present, the question remains unresolved. Another fascinating discussion concerns randomness. Computers often generate random numbers using algorithms. These sequences appear random but actually follow precise rules. Quantum mechanics introduces something different. According to current understanding, certain quantum events appear fundamentally random. Some supporters of simulation theory speculate that quantum randomness resembles algorithmic processes. Most physicists disagree. Experiments consistently support genuinely quantum behavior rather than hidden computational shortcuts. Still, research continues. Perhaps future discoveries will reveal deeper structures. Perhaps not. One interesting comparison involves chess. A computer analyzing every possible chess game would require unimaginable resources. Instead, modern chess programs evaluate only the most promising possibilities. Similarly, perhaps the universe computes efficiently rather than exhaustively. Again, this remains an analogy, not evidence. Many of the ideas surrounding simulation theory borrow inspiration from modern computing because computers provide the closest technology humanity currently possesses. Future generations may discover entirely different forms of information processing, concepts we cannot yet imagine. History repeatedly reminds us how limited present-day imagination can be. The first computers used vacuum tubes. Few predicted smartphones. Few anticipated artificial intelligence. Likewise, our current understanding of computation may represent only the beginning. Another important point often overlooked is this. Simulation theory makes remarkably few unique predictions. Most observed phenomena already possess explanations within conventional physics. Relativity, quantum mechanics, particle physics, cosmology. Simulation theory generally interprets these discoveries differently rather than replacing them. This explains why many physicists remain cautious. The theory is philosophically fascinating. Scientifically, it remains largely speculative. Even so, its influence continues growing. Not because evidence demands it, but because it encourages deeper questions about information, consciousness, and the nature of existence. Sometimes asking bold questions leads to unexpected discoveries, even if the original idea ultimately proves incorrect. History offers many examples. Researchers searching for one phenomenon often uncover another entirely different. Perhaps the greatest contribution of simulation theory lies not in proving we live inside a computer, but in forcing us to reconsider what reality actually is. And that brings us to another fascinating subject. Long before philosophers proposed digital universes, storytellers imagined worlds where reality itself was an illusion. From ancient myths to modern cinema, the idea has captivated human imagination for centuries. The next chapter explores how fiction helped shape one of the most intriguing philosophical ideas of our time. Part 8. Long before computers existed, long before artificial intelligence, and centuries before anyone imagined digital worlds, storytellers were already asking a remarkable question. What if reality is not what it seems? Few ideas have captured the human imagination more completely. Throughout history, myths, novels, films, and television have repeatedly explored hidden realities lying beneath everyday life. Although these stories differ greatly, they share one central theme. The world we experience may be only a small part of something much larger. One of the earliest examples appears in ancient Greece. As discussed earlier, Plato's allegory of the cave describes prisoners who mistake shadows for reality. For over 2,000 years, philosophers have used this story to illustrate the limitations of human perception. Modern readers often recognize striking similarities between Plato's cave and simulation theory. The cave wall becomes a computer screen. The shadows become digital information. The deeper reality remains hidden. Whether Plato intended anything resembling modern simulations is doubtful. Yet his thought experiment continues feeling surprisingly contemporary. Centuries later, writers began imagining artificial worlds created through technology rather than mythology. One important milestone came in 1964 with Daniel F. Galloway's novel Simulacron 3. The story described an entire simulated city populated by conscious digital beings unaware that their world was artificial. The novel later inspired the films World on a Wire and The 13th Floor. Many ideas explored in these works closely resemble modern discussions of simulation theory. Another influential film arrived in 1998. Dark City. In this visually striking story, mysterious beings continually reshape an artificial city while altering its inhabitants' memories. Reality changes overnight. The population remains unaware. Although different from modern simulation theory, the film explored similar questions about memory, identity, and perception. Then, in 1999, one movie transformed these philosophical ideas into a worldwide cultural phenomenon: The Matrix. The premise appeared deceptively simple. Humanity unknowingly lives inside an enormous computer simulation while machines harvest biological energy. The simulated world appears completely real. Only a small group of individuals discover the truth. The Matrix became one of the most influential science fiction films ever made. Its visual effects revolutionized filmmaking. Its philosophical questions reached millions of viewers. The famous choice between the red pill and the blue pill entered popular culture as a symbol of choosing uncomfortable truth over comforting illusion. Interestingly, the creators drew inspiration from numerous philosophical traditions: Plato, Descartes, Buddhist philosophy, cyberpunk literature, modern computer science. The result introduced an entire generation to ideas that had previously remained largely within philosophy departments. Although highly fictional, The Matrix dramatically increased public interest in questions about reality itself. Another fascinating film, The 13th Floor, explored nested simulations. Characters gradually discover that their world is artificial. Then learn that the world containing their creators may also be simulated. The concept closely resembles philosophical discussions about simulations existing inside simulations. The film asks an unsettling question: if one simulated civilization creates another, how could anyone know which level of reality they occupy? Television soon embraced similar themes. Series such as Westworld explored artificial beings gradually becoming self-aware. The hosts initially believed their world represented ordinary reality. As their understanding evolved, they began questioning the nature of consciousness, identity, and free will. Although focused primarily on artificial intelligence rather than simulation theory itself, Westworld examined many of the same philosophical questions. Another influential franchise is Tron. Here, humans enter digital environments populated by conscious computer programs. The films portray software as living societies with laws, politics, beliefs, and struggles. Again, fiction anticipates philosophical questions now discussed by researchers studying artificial intelligence and digital consciousness. Video games have become perhaps the most immersive exploration of simulated realities. Modern players routinely inhabit detailed virtual worlds for hundreds of hours. They form friendships, build communities, explore cities, develop emotional attachments to digital environments. The boundaries between physical and virtual experience continue becoming increasingly sophisticated. Virtual reality pushes immersion even further. Wear a headset. Pick up motion controllers. Within moments, your brain responds naturally to entirely artificial surroundings. The technology remains relatively young. Future generations may produce experiences almost indistinguishable from ordinary perception. Science fiction has repeatedly imagined exactly this future. One reason simulation theory resonates so strongly today is that humanity has begun creating increasingly convincing virtual worlds ourselves. Every technological advance makes the concept slightly easier to imagine. Still, fiction often simplifies scientific ideas. Movies require dramatic conflict. Heroes, villains, escapes. Simulation theory, as discussed by philosophers, contains none of these elements. Nick Bostrom's argument does not involve evil machines, nor hidden agents, nor secret rebellions. It concerns probability, computation, and philosophical reasoning. Popular culture understandably transforms abstract ideas into compelling stories. Another fascinating observation concerns the influence running in the opposite direction. Science fiction has repeatedly inspired real science. Engineers cite Star Trek as inspiration for mobile communicators and tablet computers. Arthur C. Clarke imagined communication satellites decades before they became reality. Jules Verne described submarines and moon voyages long before the necessary technology existed. Imagination often precedes innovation. Today's fiction may inspire tomorrow's engineers. Perhaps simulation theory will encourage future breakthroughs in computing, artificial intelligence, neuroscience, or quantum information, even if the hypothesis itself ultimately proves incorrect. Stories possess tremendous power. They allow humanity to explore possibilities before technology catches up. Another reason simulation theory has become so popular is psychological. It offers a modern framework for timeless questions. Who are we? Why are we here? What is consciousness? Is there a purpose behind existence? Earlier generations often approached these questions through religion or philosophy. Today, many people explore them through science and technology. Simulation theory occupies an unusual position. It speaks both languages. Scientific enough to interest physicists. Philosophical enough to inspire endless debate. Yet after exploring philosophy, technology, physics, artificial intelligence, and popular culture, one final question remains. Suppose tomorrow we somehow prove that reality truly is a simulation. What would actually change? Would morality still matter? Would love become less meaningful? Would consciousness lose its importance? Or would life remain every bit as real to those experiencing it? The final chapters explore these profound questions and ask whether simulation theory ultimately changes anything about what it means to be human. Part 9. Imagine waking tomorrow morning to astonishing news. Scientists announce that they have discovered undeniable proof. The universe is, in fact, an artificial simulation. After the initial shock, what would actually change? Would gravity stop working? Would the sun suddenly disappear? Would your family become less real? Would your memories lose their meaning? Perhaps surprisingly, the answer to all of those questions is no. Your world would remain exactly as it was the day before. The laws of physics would continue operating. Life would continue. The only thing that would change would be our understanding of reality. This observation reveals something profound. Simulation theory is not merely about computers. It is about philosophy. It forces us to reconsider some of humanity's oldest questions. What is real? What is consciousness? What gives life meaning? For thousands of years, philosophers have debated these ideas. Simulation theory simply presents them in a modern technological form. One of the first questions concerns free will. If reality is programmed, are our choices predetermined? Imagine playing an open-world video game. The environment follows programmed rules. Gravity functions consistently. Weather changes. Characters interact. Yet within those rules, players remain free to make countless decisions. Supporters of simulation theory sometimes suggest reality could operate similarly. The underlying framework might be programmed. Individual choices could still remain genuine. Others disagree. If every event ultimately follows code, perhaps free will is only an illusion. This debate did not begin with computers. Long before simulation theory, philosophers questioned whether free will could exist in a universe governed by physical laws. Simulation theory simply gives the discussion a new vocabulary. Another profound question concerns consciousness. Suppose we truly are simulated beings. Would our thoughts be less authentic? Would emotions become artificial? Most philosophers answer no. Pain experienced within a simulation still feels like pain. Joy still feels like joy. Love still feels like love. Conscious experience remains meaningful regardless of the substrate producing it. Consider dreams. While dreaming, experiences often feel completely real. You may experience fear, wonder, excitement. Even after waking, the emotions remain genuine despite the dream's imagined environment. Likewise, if reality were simulated, the experiences themselves would remain authentic to those living them. Another fascinating issue involves morality. Would ethical behavior still matter? Some critics worry that simulation theory encourages nihilism. If nothing is real, they argue, nothing matters. Most philosophers reject that conclusion. Relationships matter because conscious beings experience them. Kindness matters because it affects others. Suffering matters because it is genuinely felt. Whether reality ultimately consists of atoms or computer code does not eliminate moral responsibility. If anything, a universe containing conscious beings deserves compassion regardless of its foundation. Then comes one of humanity's oldest questions. What about religion? Some people see striking similarities between simulation theory and traditional ideas of creation. A higher reality, intelligent creators, purpose. Others emphasize the differences. Simulation theory does not necessarily involve supernatural beings. Its creators, if they exist, might simply be advanced biological or artificial civilizations. Science itself remains neutral. It investigates evidence. Religious beliefs address broader questions concerning purpose, meaning, and spirituality. Some individuals find harmony between the two perspectives. Others keep them entirely separate. Both approaches continue being discussed. Another remarkable aspect of simulation theory is how it changes our view of humanity. For centuries, humans believed Earth occupied the center of the universe. Science gradually expanded our perspective. Earth became one planet among billions. Our galaxy became one among hundreds of billions. The observable universe itself may represent only a tiny fraction of reality. Simulation theory proposes yet another expansion. Perhaps even our universe is not ultimate reality. History repeatedly teaches the same lesson. Reality is often larger than we first imagine. This realization encourages humility. Every generation has believed it understood the universe. Every generation eventually discovered deeper mysteries. Perhaps ours will be no different. Simulation theory also raises fascinating questions about purpose. Why would a simulation exist? If creators exist, do they observe us? Care about us? Ignore us? No scientific evidence currently answers these questions. Any proposed motivation remains speculative. Some suggest research. Others entertainment. Others education. Perhaps the simulation has no specific purpose at all. Science cannot presently distinguish among these possibilities. Perhaps the most important lesson concerns uncertainty. Modern science does not claim certainty where evidence remains incomplete. Simulation theory remains an intriguing philosophical hypothesis. not an established scientific fact. No experiment has demonstrated that our universe was programmed. No observation requires simulation as its explanation. Current physics successfully explains an enormous range of phenomena without invoking external programmers. At the same time, science also teaches openness. Ideas should not be rejected simply because they sound unusual. They should be evaluated carefully, objectively, through evidence. History reminds us that many extraordinary ideas initially seemed impossible. Heliocentrism, continental drift, quantum mechanics, black holes, gravitational waves. Each eventually earned acceptance because evidence accumulated. If someday evidence supports simulation theory, science will investigate it. If evidence never appears, the idea will remain an interesting philosophical possibility. Either outcome contributes to knowledge. Perhaps the greatest contribution of simulation theory is not that it proves anything. Rather, it encourages humanity to ask deeper questions. What is consciousness? Why does mathematics describe the universe so beautifully? What is information? Could reality possess layers beyond those we currently understand? These questions inspire research across physics, computer science, artificial intelligence, neuroscience, philosophy. Sometimes asking impossible questions leads to remarkable discoveries. Even when the original question receives an unexpected answer, only one chapter remains. After exploring philosophy, computing, physics, consciousness, and the search for evidence, we return to the biggest question of all. What does simulation theory ultimately teach us about ourselves? And about humanity's endless search to understand reality? Part 10. Since the beginning of civilization, humanity has looked toward the heavens and asked the same question. What is all of this? The stars, the planets, the vastness of space, life itself. Every generation has searched for answers. Ancient civilizations explained the universe through mythology. Later generations turned to philosophy. Then came science. Each new discovery expanded our understanding of reality. The Earth was not the center of creation. The Sun was only one ordinary star. Our galaxy became one among hundreds of billions. Space itself was found to be expanding. Time proved flexible. Matter became energy. Particles behaved like waves. Reality grew stranger with every century. Simulation theory represents the latest chapter in that remarkable journey. It asks an extraordinary question. Could reality itself be artificial? Not fake. Not meaningless. But intentionally created through technology beyond anything we currently understand. Whether that idea ultimately proves correct remains unknown. Yet the journey toward answering it has already taught us something valuable. It has forced scientists, philosophers, and technologists to work together in ways rarely seen before. Computer science meets cosmology. Artificial intelligence meets philosophy. Quantum mechanics meets information theory. Questions once belonging solely to science fiction are now discussed in universities and research laboratories around the world. That alone makes simulation theory historically significant. Throughout this documentary, we have separated established scientific knowledge from speculation. We explored Plato's cave and ancient philosophy, Nick Bostrom's simulation argument, the astonishing growth of computing technology, virtual reality, artificial intelligence, the possibility of digital consciousness, the physics of information, the Planck Scale, the Holographic Principle, quantum mechanics, déjà vu, the Mandela effect, and the philosophical consequences of living inside a simulated universe. Some of these subjects rest upon decades of experimental evidence. Others remain theoretical. Some belong primarily to philosophy, others to psychology. Keeping these distinctions clear is essential. Science advances by asking bold questions, but it progresses only through careful evidence. At present, no scientific experiment has demonstrated that we live inside a simulation. No observation requires simulation theory to explain it. The standard model of particle physics, general relativity, quantum mechanics, cosmology. These theories continue describing the observable universe with extraordinary success. Simulation theory remains an intriguing possibility, not an established conclusion. That distinction may seem disappointing. In reality, it represents one of science's greatest strengths. Scientists are willing to say, "We do not yet know." Those 4 words have driven nearly every great discovery in human history. Whenever researchers reached the limits of knowledge, new questions emerged. Those questions inspired new instruments, new experiments, new theories, new generations of explorers. Perhaps simulation theory will eventually follow that same path. Perhaps future discoveries in quantum gravity, artificial intelligence, or cosmology will reveal evidence supporting the idea. Or perhaps entirely new discoveries will explain today's mysteries without requiring simulated realities. Either possibility represents progress. One fascinating lesson repeatedly appears throughout history. Human intuition is often wrong. The Earth feels motionless, yet it races around the sun. Time appears constant, yet it slows near immense gravity. Space seems empty, yet quantum fields constantly fluctuate. Reality has repeatedly proven stranger than common sense. Could simulation theory become another example? Perhaps. Perhaps not. Only evidence will decide. Another important lesson concerns technology itself. Humanity has progressed from mechanical calculators to artificial intelligence within a remarkably short period. Virtual worlds become more convincing each year. Machine learning continues advancing rapidly. Quantum computing remains in its early stages. No one can confidently predict what civilization may achieve centuries from now. Our descendants may develop technologies appearing almost magical by today's standards. History urges caution whenever we declare something impossible. The future often surprises us. Yet perhaps the greatest question raised by simulation theory is not technological at all. It is deeply human. If reality were simulated, would life lose its meaning? Most philosophers answer no. Meaning arises from conscious experience, from relationships, curiosity, creativity, compassion, discovery. Whether reality ultimately consists of atoms, quantum fields, information, or computer code, the experiences we share remain profoundly important. The birth of a child, the beauty of music, acts of kindness, scientific discovery, the night sky filled with stars. These moments matter because they are lived, not because of the material from which reality is constructed. Perhaps that is why simulation theory continues captivating millions of people. It combines humanity's oldest philosophical questions with our newest technological achievements. It reminds us that every generation inherits mysteries from those who came before, and leaves new mysteries for those yet to come. The search itself becomes part of what makes us human. We question. We investigate. We imagine. We test. We learn. Whether the universe is fundamental or simulated, those qualities remain unchanged. As our telescopes peer farther into space, as our particle accelerators probe deeper into matter, as artificial intelligence grows more sophisticated, and as our understanding of consciousness slowly expands, New discoveries will undoubtedly reshape our picture of reality once again. Perhaps one day humanity will answer the question that inspired this entire journey. Are we living inside a computer simulation? Until that day arrives, the idea remains one of the most fascinating possibilities ever proposed. Not because it has been proven, but because it challenges us to think beyond the limits of ordinary experience. It reminds us that reality may still hold astonishing secrets, and that the greatest discoveries often begin with a single question. What if everything we know is only part of a much larger reality? Whether that reality is physical, digital, or something beyond our current imagination, the search continues. And so does humanity's endless desire to understand the universe and our place within it.